Hi there. This is the video lesson covering electron configurations. Electron configurations are a sort of code that chemists use to tell other chemists where exactly the electrons are in an atom. If we look at the periodic table and we look at calcium right here, calcium, we can see by the atomic number of 20, has 20 electrons. Now, knowing the total electrons is important, but oftentimes it's more important to know exactly where those electrons are. And if you remember, we talked about the Bohr model last unit. The Bohr model is the one with the rings, and those rings are energy levels. Well, you may have wondered, or you may not have, why the periodic table is shaped the way it is. It's not just a square. You know, it's kind of taller over on the left, kind of taller over on the right, skinny in the middle. Well, that shape corresponds to the structure of the atom. So one of the reasons it's shaped like that is because it gives us information about the atoms of the elements on the periodic table. So if I'm going to bring that periodic table up again, one thing that corresponds between the periodic table and the structure of the atom is the rows. So the rows on the periodic table are equal to the rings in the atom. So again, picture that Bohr model that we talked about last unit. It has the nucleus in the center, and then it has the rings around the center, and on those rings are the electrons. Well, the rows correspond to the rings. So if I look at calcium here, it's in the 1, 2, 3, 4th row. Well, that means that atom, a calcium atom, has 4 rings. If I look at magnesium right above it, that's in the 3rd row. That atom would have 3 rings. If I look below calcium, strontium, Sr, that's in the 5th row, that would have 5 rings. So that's just one instance where the structure or the shape of the periodic table gives us information about the structure of the actual atom. I'm not going to go through all these notes, but I'm going to skip around a little bit. I do expect you to read them all and know them all, but some of them are pretty kind of self-explanatory, just a matter of reading. This diagram here that I'm showing you kind of looks like a colorful periodic table. It is what I call the roadmap for writing electron configurations. So you're going to want to know this. I'm not going to give you this colorful thing, periodic table, on the test. You're going to want to know this pattern. And as you use it more, you'll realize it's not really all that tough to remember. The first 2 columns are the S block. The middle section is the D block. The section over here is the P block. And if you notice, helium up in the upper right corner, while it hangs out by the P block, it's actually part of the S block over here. Unfortunately, this picture shows it in green. I think it would be a lot better if it showed helium, the 1s here, in purple to show that it actually kind of it belongs over here in the S block, but it hangs out with the P block. So then we have the P block there and then the F block. And what this is, it's like a roadmap for writing electron configurations. So let me just go through the notes just real quick, point out some important things. Like I said before, the periodic table tells us how many electrons are arranged, or how the electrons are arranged in a particular atom. That's one reason it's shaped so strangely. Remember, the atomic number is the number of electrons. As the atomic number increases, the number of electrons increases. And these electrons are added into rings that we're calling energy levels. Now, orbitals are regions where electrons are most likely to be found. And we have 4 different types of orbitals: S, P, D, and F. And if you notice, that's also the name of the blocks on the periodic table diagram here. So these orbitals are kind of like sublevels in those rings. Think of it that way. It's probably the most simple way to think about it. It is more complicated than that, but at this point, I think it's just best to think of them as kind of sublevels within that energy level. So the first energy level only has one sublevel. That first ring only has S. The second ring has two, has S and P. The third ring has three orbitals, or three sublevels, S, P, and D. Fourth energy level would have 4, and so forth. I am going to skip over that real quick. Actually, we'll talk about this bullet point here. An s orbital holds 2 electrons. Look back at our diagram here. If we look at the s block here, the s block is 2 columns wide. So it's got 2 boxes in each row. Down here it says the p orbital holds 6 electrons. Well, in a row of the p block, how many boxes are there? 1, 2, 3, 4, 5, 6. And d orbital holds 10. And if we count the d block, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So again, the periodic table, those boxes correspond to the number of, or those places on the periodic table correspond to the number of electrons that particular atom has and how they're arranged. We'll come back to that. The 2n2 rule, if I ever ask you, okay, third energy level, how many electrons can it hold total? Well, you'd put 3 in for n, so 3 squared, 3 times 3 is 9, 9 times 2 is 18. So the third energy level can hold 18. Did I just say 19? Well, let's start that over. If we have the third energy level, I put n in for the energy level, so 3. Wow. Okay, I'm just going to start the 2n2 rule all over. Sorry about that. The 2n2 rule. If I ask you how many electrons an energy level or a ring can hold, you can use the 2n2 rule to figure that out. So if I say, how many electrons total can the third energy level hold? Well, you look here, you put 3 in for n, because it's a third energy level, so put 3 in for n, so 3 squared, 3 times 3 is 9. 9 times 2 is 18. So the third energy level can hold 18 electrons. Another way to figure that out is we count out the number of boxes that have the big 3 in front. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's two different ways to kind of come at the same answer. The 2n2 rule is just a little quick mathematical trick. I will let you read the last of those notes here. I want to get to some examples and show you how to actually do this. So, Mg. The way we write the electron configuration for Mg, the first thing I'm going to do is I'm going to look at my periodic table and I'll find Mg. It's right here. It's the third row down, second one in. Then I'm going to look at my road map. And I said the third row down, second one in. So right here. So now, what I'm going to do is I'm going to start back at the very beginning of the periodic table. One thing the Aufbau principle here says, it's building up. So you start at the beginning and you build up to the particular atom that you're looking for. So let me, 1 second. Okay, so again, Mg, it's right here. Third row down, second element in. And what I'm going to do is I'm going to start back at the beginning of the periodic table. Start at hydrogen, and I'm going to build up, going across, kind of like a typewriter. You go straight across. When you get to the end of the row, go down to the next row, straight across, go down to the next row, straight across, until I get to Mg, which is right here. And all I do is I write down that code. So, the way I would write the electron configuration for Mg is 1s, and if I look up here, how many 1s boxes are there? There's a 1s box here, and then there's a second one here. So, I write a little 2. It looks like it's an exponent, and a lot of people are tempted to say 1s squared. It's not, it's just 1s2. It just happens to be a superscript, up like an exponent. It's not actually an exponent though. So 1s and then 1, 2, that got us here. We're done with this row. We go down to the next row. The code here for that second row is 2s. So that's the next thing in my electron configuration is 2s. And we count how many 2s boxes there are. 1, 2. So again, I put a little 2 up here. I'm done there. I go straight across. The next code I get to is 2p. So 2p. And I count how many boxes there are. 1, 2, 3, 4, 5, 6. So it's 2p 6. I'm done with that row. I go down. The next code I hit is 3s. And remember, magnesium is the second one in, so 1, 2 gets me to magnesium. So that right there, 1s2, 2s2, 2p6, 3s2 is the electron configuration for magnesium. I'm going to do one more here, and then you'll have a chance to try a couple. Let's do chlorine. Again, we find chlorine in a periodic table. It's over here on the right side. It's the third row down, second one in from the end. So, third row down, 1, 2, 3, second one in, right here. This is where chlorine is. So again, I'm going to start at the beginning of the periodic table and count up to this spot right here. So beginning of the periodic table, we have 1s, and again there's 2 of those boxes. So my electron configuration is 1s2. That gets me done with that row. And I'm done with that row. Go down to the next row. 2s, and I see 1, 2 boxes. So 2s, 2. Go straight across, and I hit, next code I hit is 2p, and there's 1, 2, 3, 4, 5, 6 boxes there. So 2p6. Next I hit 3s, because I'm done with the second row. I go down to the third row. 3s, and there's 1, 2. So 3s2. And lastly, 3p, and if you remember, chlorine is right here. So 3p is the next code I hit. 3p, 1, 2, 3, 4, 5 gets me to chlorine. So 3p 5. That is the electron configuration for chlorine. So I'm pretty much out of time here. So I will stop this video and I will continue on with the next video.